than chapter 9. Uh, in one sense, it's much easier because we're not dealing with air and so many different characteristics and all that. We have only one cycle, and of course, we modify that cycle as we go through it, but the base of the cycle never changed. So, chapter 10 called Vapor Power Cycle. In the industry, we call it steam power plant. Now, I'm going to draw the equipment diagram, which is pretty similar to what you have seen before. Let's see. Okay. Now here before we had in chapter 9, we had a compressor. Now we have pump. By the way, the working fluid is water. And that water undergoes phase changes. Now, what that means in chapter 9, no matter what we did with air, air remained the same. We couldn't change its phase. However, water is different. If we cool it down, it becomes ice, becomes solid. That's one phase change. If we heat it up, that water becomes vapor. And that basically completely changes the phase of the water. It gets to a point, it acts like a gas. It's not a gas, but considered to be so high temperature and high pressure. And that is a vapor, and that's what we use to run a power plant, to run a steam power turbine. So remember that. So the working fluid is water for this chapter, and that water goes on a phase changes. Now, before we had a compressor, we cannot use compressor because we cannot move liquid with a compressor. That's why we use pump. Now here, if you remember, we had a combustion chamber. Now we replace the combustion chamber with a boiler. And well, this is what 0.2, and that would be 0.3. So this becomes our Q in. Now here we have our steam turbine. That's where we get the work out. Now at 0.4, if you remember, we had a heat exchanger to get back to 0.1. Now this time, the heat exchanger is called condenser. That's where we get our Q out. Condenser is a form of a heat exchanger that we remove the heat from the system to get back to our source, which is 0.1. Once again, our direction is clockwise. So that is the equipment layout. And this is how we're going to use in chapter 10. So basically what we did, we replaced the compressor with pump. We replaced the combustion chamber with the boiler, and usual, we start with Carnot cycle. And you know the processes of the Carnot cycle. We know that process 1 to 2, that's 1 to 2, is isentropic compression. That never changed. Then, according to Carnot, process 2 to 3 is isothermal. Heat addition, T2 is equal to T3. 3 to 4, once again, isentropic expansion. S3 is equal to S4, and process 4 to 1, again, isothermal heat rejection. That's T4 equal to T1. These are the 4 processes. Now, in chapter 10, we do not have PV diagrams. So we have only one diagram, and that's a TS diagram. And TS diagram is extremely crucial in order to solve the problem. So the TS diagram for this, again, this change of the phase for the liquid or for the water, you've seen it in MAE330 or thermodynamic bond. So we have a dome to represent the phase changes. Now, what you need to know about this dome, again, this is just refreshing your memory. Everything that, if we look at this, center, draw the line in the center of the dome, everything on this side of the curve of the dome, any point located on that is called saturated liquid line. So this line represents the saturated liquid. Everything to the left of that is called compressed liquid. Now, as you have learned before in your previous course, we do not have a separate table for compressed liquid. So there is only one table that has all saturated liquid, including compressed liquid, because what we did, basically trying to create a table for compressed liquid, we realized the changes between the value of enthalpy or entropy or any thermodynamic parameters with the saturated liquid, it's almost identical with a very, very, very small percentage of difference. So that's why we decided, instead of having 2 separate tables, one for saturated liquid and one for compressed liquid, we have only one table, and every point located in this side, we're all going to look at this saturated liquid table. That's just something that you know. Now, anything that on this side or this part of a curve or a dome, if you will, this is saturated vapor line. Now, anything on the side of that line, outside of this curve, is called superheated region or superheated area. So everything here is a superheated, everything here is compressed liquid. On those, at that line is a saturated liquid line, and any point on this line is a saturated vapor line. Now, any point that is located under the dome, it's considered as a mixture. This is mixture of liquid and vapor. Now, as you know, the mixture of the liquid and vapor has a quality, and that quality, we call it X. This quality shows how much vapor or how much liquid and vapor are basically or together in order to get this mixture. So to solve a problem, we always need to have the quality of the mixture. So the quality X is between 1 and 0. Any point on this red side, the X value is equal to 0. So any point located on saturated liquid line, the X value, the quality is 0. Any point on a saturated vapor line, the quality is X is equal to 1. Obviously, if X greater than 1, that means the point is in a superheated region. If X is less than 0, that means the quality is in compressed liquid. At that time, we don't have a mixture. So the only time that we have a mixture is this condition. X will be between 0 and 1. So that is basically the TS diagram that we're going to work with. Do you have any question on this? This is, you've seen this in, thermodynamic 1. I'm just bringing it up to your attention because we're going to use this and I don't want any confusion. Is there any question? Because I'm going to erase all of this to do the TS diagram for the corner circle. It's so terrible that I cannot see you and I have no idea. Okay. Since you don't have any questions, so I'm going to erase all these extra things that I put here. All right. Now, if you follow what Carnot cycle is saying, that we have a process 1 to 2 isentropy. So that means there is a 1 here going up to 2. Then from 2 to 3 is at constant temperature. From 3 to 4 is isentropy. going down. And then coming back to point 1. So that would be my Q in. This is the Q out. Of course, this is work of the turbine, and this is work of the pump. Once again, you can see that we cannot add heat to any system without changing the temperature. Same thing, we cannot reduce, we cannot cool down anything without reducing the temperature. So that's, again, the two flaws onto this system. Now, the other flaws into the system is point 1. As you notice, point 1 is located at mixture region. The pumps, by the nature of the beast, cannot, absolutely not, pump vapor and liquid mixture. We designed a compressor to basically pressurize air and gases. We designed the pump to pressurize liquid, including water that we're going to use here. The same way that we cannot introduce liquid to the compressor, here we cannot introduce vapor to the pump. So that's the third part of the flaw into the Carnot cycle. That's why it doesn't work. So, of course, now that we talk about the processes, we also have to talk about phases, which there's no need to discuss this one, but I'm going to erase all of that and I'm going to talk about the real cycle, and that's how we're going to start. Do you have any question here? Okay. So Carnot cycle is out. Now, chapter 10 starts with ideal, simple, Yankee cycle. That's the first one we're going to use. Now, I'm going to do the equipment arrangement a little different. So this is our pump. This is source of the water at point 1. This is not boiler. This is not a steam turbine. Now here is our condenser. Going back to point 1. Same thing, just rearrange it a little bit. So that's how you're going to see it. Once again, we have a source of water. This source could be a well, could be a river, could be regular, city water coming through the pipe. So that's our source. We pressurize it. We send it to the boiler. Consider boiler like your hot water heater at home. but about maybe 1,000 times bigger than that. That's the size of a boiler. So underneath the boiler, like your hot water heater that you have a gas that it's burning and giving you the hot water, we have the same scenario here. We can use natural gas. This is what we use today. The old days, they used to have, crude oil. And there are some coal running power plant, the fuel that it's used to, to run the boiler is coal. In case of a nuclear power plant, you have the same situation. The only difference is the fuel instead of natural gas or crude oil or coal is a nuclear rod, and that's what they call nuclear power plant. But the concept is all the same. Again, we're going clockwise, that's our direction. So the simple ranking cycle has these processes. Process 1 to 2 never changes. Isentropic compression. S1 is equal to S2. Process 2 to 3, isobaric heat addition. P2 is equal to P3. Process 3 to 4, once again, isentropic expansion. That never changes. S3 is equal to S4. Finally, process 4 to 1, it's isobaric heat rejection, meaning P4 is equal to P1. These are the 4 processes. Now, to do a TS diagram, I'm going to start my point 1 right in the saturated liquid line. So I go isentropy up. Now, as you notice, I just tilted it to the left a little bit because I want you to see it. In reality, this should be perpendicular to the S-axis, but I just tilted a little bit so you can distinguish that line and the curve, because if I do it straight up, they're so close that created confusion. So that's my point 1, isentropically going up to point 2. Now between 2 and 3, the heat addition is exponentially happen, and that's point 3. So the pressure at point 2 and 3 are the same. Then I'll come down isentropically to point 4. And then connect it back to point 1. So in this scenario, again, this is my work of a pump, work of a turbine, my Q in, and my Q out. Now, a couple of things I want to just share with you. In the industry, we call the Q in we call it Q of the boiler. And we call the Q out Q of the condenser. So you might see this in your, some of the problems. So I don't want you to be, confused by it, or I don't want that to be strange. So now that we have the processes and we have the TS diagram based on the coordinate diagram, we want to know what are the phases, because at point 1, we had a saturated vapor, now we have compressed liquid, unsaturated liquid, we have a compressed liquid, now we have saturated vapor, and now we have mixture. These are the different phases within this cycle. So the same way that we have processes, we have phases. So we call that phase 1 is saturated liquid. Phase 2 is compressed liquid. Phase 3 is saturated vapor. Finally, phase 4 is a mixture of liquid and vapor. So these are the 4 phases that we go through this. Any questions? No. Now I want you to write this statement, because this is going to help you a lot if you understand that. Throughout this chapter, the last point of any cycle is in mixture region. There is no ifs or but or no exception. In this case, we have 4 points. Last point is 4, and as you can see, is in the mixture. There is no way that the last point of your cycle, any cycle that you develop will be outside in a superheated region, or will be located on this curve for a saturated vapor. Never, ever going to happen. This is some mistake that a lot of people do when they do the homework of taking the second test, putting 0.4 outside or putting 0.4 right at the saturated vapor. That will never, ever happen. The last point of a cycle, always, always, always going to be in the mixture. If we have 12 points, the point number 12 is the last point. Guess what? That point definitely is going to be, in a mixture area. So as we go through and you see a lot of these problems, you'll see that we always have a last point in that, mixture region. But I just want to bring that to your attention. That's how it works. So this is ideal simple ranking cycle. And an ideal simple ranking cycle, point 3 is located at the saturated vapor line. Now we're going to do just a simple ranking cycle. Same equipment arrangement. The TS diagram will be different. So I'm going to come up here, going up exponentially to 0.3 and coming down to 0.4. Now, these processes will never, ever change. Any compression, any expansion happen isentropically. You've seen that before, and we told you that's true, throughout this course. Now, for chapter 10, the entire chapter 10, any heat addition, heat rejection happen at a constant pressure. Simple as that. So that makes it much easier. You don't have to worry about like an Otto cycle was different than a diesel cycle was different than Brayton cycle. Here, you have a cycle that has these 4 processes throughout chapter 10. No matter how much we modify, no matter what we do to it, that remains the same. That's something for you to, it's good to know. Now, here, as you can see, as far as the phase is concerned, phase 1 remained the same. Phase 2, again, remained the same. The only difference this time, we have phase 3. Our phase 3, it's in superheated region. Phase 4, as we said before, always going to be in a mixture of the liquid and vapor. That will never change. So that's the only change we made. And as we do some exercise, you'll see the reason we get it to superheated so we can have higher, efficiency for the entire cycle. Any questions? It's a huge difference. The difference is when I go to the superheater, my temperature is going to go high. Therefore, I have better, as you can see, I have higher work out. Look at my work of a turbine. Before, this was the scenario. Point 3 was here and point 4 was there. And look. Basically, we're never ever going to use ideal Rankine cycle. You can call it theoretical because it's not to our advantage to use this. All our steam power plants work on the superheated region. Yeah, that's why we call it ideal. Ideally or theoretically, this is how it works. Now, I want to show you how we're going to solve problems for these 2 cases, both ideal and simple Rankine cycle. So, what I'm going to do, I'm going to erase all of these. And show you how we solve the problem. Now, to start with, like what we have done before, we always start at state 1. So at state 1, now, one thing you need to, one thing you need to understand, in chapter 9, when we went to the table to find out the values of, various parameters that we were looking for, thermodynamic parameters like enthalpy or internal energy, we just needed one thing, and that was the temperature. And the temperature was converted to degree Kelvins or degree Rankines. Here in chapter 10, we need 2 point of references. in order to get various values. And the temperature, by the way, that we use here, it's all degrees Celsius or Fahrenheit. We don't have to convert it because the reason we converted in chapter 9, because we were dealing with ideal gas equations. Here, we don't have ideal gas equation. So therefore, we don't have to worry about converting it to degrees Kelvin or Rankine. So at state 1, I need to have 2 points of reference. Now, keep in mind, in this scenario, we have P1 equal to P4, and we have P2 equal to P3. Don't forget that, constant pressure. It doesn't look like it, and the reason for it, this is a three-dimensional. The third dimension is the pressure, which you don't see it here. We're trying to show it in a two-dimensional graph, which is these are the two dimensions that we need to know. So pressure of 4 and 1 are the same, the temperature of 4 and 1. Don't forget that. Pressure of 3 and 2 are the same, the temperature of 3 and 2, which is very obvious here. So at state 1, I have pressure P1, whatever it gave me. Then I have X1, quality at point 1, equal to 0. These are 2 points of reference. I go to table. What table are we going to? Saturated liquid table. We have 2 tables here. One is saturated liquid, other one is superheated table. These are the 2 tables you have. At the saturated table, I look at H1, which is H of F. Now, when you go to saturated liquid table, if you look at it at the top, you have V of F, you have V of G, you have S of F, S of G, S of F of G, H of F, H of G, H of F of G, and so on and so forth. So you have all these values. So you look at the pressure line and you just keep on going and find whatever you are looking to find. Now, we are in the liquid side. F presents the fluid or liquid. So H of F, when we found it from the table, that comes as H1. That would be H1 value. While I'm there, I'm going to find V1, which is again V of F. And I tell you why, because I'm going to use it for step 2. Now, coming to step 2, there are 2 ways doing it. One way is basically pretty hard, and that's how it's, don't pay attention to this one. Using P2 and S1 being equal to S2, that means I have to find S1, which is S of F, in the first place. Then, based on these 2 values, and based on the interpolation, I found H2 value. That is a painful process. Why should I do that? So, as an engineer, we need to find an easy way out. What is the easy way out? I write work of a pump is a delta H plus the equipment, H2 minus H1. Then I go back to my fluid mechanics. I remember how they defined work of a pump. Work of a pump was the V, the volume at the base of the pump, which is V1, right there, times the delta P, the pressure between 1 and 2, because I'm taking this water at this pressure, taking it to that pressure. So P2 minus P1. Now, H1, I already found it from state 1. V1, I found it there. P2 and P1 was given to me. What's the unknown here? There's only one unknown, and from there, I will find H2. How simple it is, without any interpolation, within a matter of few seconds, less than a minute, I can find H2. If I wanted to go that route, I had to spend 10 minutes of interpolation to find the value of H2. So why not using the easy way out? Remember that. Always do it that. Now, we go to state 3. Now, in this case, our point 3 was in the saturated vapor in case of an ideal cycle. So, therefore, I had P3 and my X3 was equal to 0. Once again, I go to regular table. This time, I find H3, which is H of G. Because now I'm at the vapor side, so I have to use H of G. And then that would be my H3. While I'm there, I also find S3, which is S of G. So that completes my state 3. Since we don't use this anymore, or this concept, I'm going to write the state 3 for the ranking cycle, simple ranking cycle. For there, I need to have 2 points of reference. I have to have P3, also P3. These are the 2 points of reference. Based on these 2 points of reference, I go to superheated table. So far, we were looking at just the saturated liquid table. Here, we go to superheated table. When you go to superheated table, you don't find H of S, H of G, or V of F, none of those. You just find S value, H value, that's it. So it's pretty easy. So you find H3 and S3. You no longer H of G or S of G or any of those. Just H3, the value of H and value of S based on these 2 points of reference. So now I gotta go to state 4. State 4 is no time consuming. For any point that is in a mixture, in both cases, it doesn't matter whether it's ideal or simple ranking cycle. For state 4, we need to do the following. At state 4, I have P4, which is the same as P1. That's my one point of reference. My second point of reference is S4 is equal to S3. Isentropic. S4 is equal to S3. Based on these 2 points of reference, I go to the table. Saturated liquid table. I will find S of F and S of F of G. Similarly, I will find H of F, H of F of G. I find all these 4 values. one of the values is known to me. See that guy, H of F? What was the pressure? The pressure point P4 and P1 is the same. So that H of F is the same as H1. So that helps you a lot. So you're only looking for 3 more values. Once you find these values, then you say the X4, the quality at point 4 you need to find. The X4 is equal to S4 minus SF divided by S of F of G. You guys remember this equation? This was like S4 is equal to S of F plus X4 times S of F of G. Or basically, forget about the point. In general, that's what it was. For H is H of F plus X times H of F of G. I rearranged that equation. So now I look at it, I have S4, which is because it's the same as S3. I have S of F, I have S of F of G. So I'm looking for X4 value. That's where I find X4. Again, always less than 1. Now that I have the quality, I use this equation. I will write H4 is equal to H of F plus X4 times H of F of G. And that's how I find my final H4 value. Because there is no table for mixture of liquid and vapor. That's why we have to find the quality. Based on that quality, then we find the value of H4. So anytime you have a point in a mixture region, you need to follow these steps in order to find the value of the H for that point. Now that I have all of these points identified, work of a pump is H2 minus H1. Work of a turbine is going to be H3 minus H4. My Q in would be H3 minus H2. And my Q out would be H4 minus H1. Nothing's changed. Delta H cross the equipment. For pump, delta H cross the equipment. For Q in, delta H cross the boiler. H3 minus H2. For a turbine, delta H cross the equipment. H3 minus H4. Q out is a delta H cross the condenser. H4 minus H1. So the difference between ideal and a basically simple rankine cycle is just the state 3. Other than that, state 1, 2, 4 remain the same as far as the approach to solving the problem. Once you have all of that, guess what? You remember I said that we have, okay, this. I said that network is Q in minus Q out. This will never change. Or work of a turbine minus work of a pump in this case. So this concept will never change as far as defining the network. For thermal efficiency, again, is the same. Network divided by Q in, or 1 minus Q out over Q in. That will never change either. So once you find these values, then you can plug it into these two equations and find the net worth and thermal efficiency. That's as simple as that. Any questions? Wait. I didn't, this is not a problem. I didn't give you any numbers. I am just showing you how to approach solving a problem. If, once I do the example, then you see what are the values that you have. Then we go to the table, then we find those values, we solve actual problem. What you see here is a breakdown of the steps that you need to take and the solutions that you need to know how to solve a problem. These are just the steps. There is no values. There's no, temperature, there is no pressure, there's nothing given. Any other questions? Okay. Now that you're so interested to know all those values, I give you an example. All right. I'm going to do a quick example for simple ranking cycle, not ideal, just a simple ranking cycle. For a simple ranking cycle, again, we need a TS diagram. That's my point 1.